It is application of Newton's second law of motion on the connected system of bodies moving on the inclined plane. We have learned about the motion of connected bodies on a flat surface while moving horizontally, and motion of connected bodies on the pulley system. Okay, now suppose the system of connected bodies is moving down or up the inclined plane whose inclination angle is theta. How may we use Newton's second law of motion to analyze the motion of this system? Here we shall consider in two cases. Case one, suppose if the system, suppose if the plane, sorry, not the system, suppose if the plane is frictionless and the bodies or system moving down the plane. Suppose if the system, if the plane is frictionless, means smooth, and the system of masses moving down the plane. Now, first of all, we have to sketch the free body diagrams for mass 1 and mass 2. We analyze the forces acting on these two masses. Our plane is inclined at an angle theta. The angle of inclination is theta, and the masses is M1 and M2 connected by a string. Now the force is acting on mass 1. It is the tension force due to this string T. Also, its weight which acting at an angle theta about the vertical. The weight M1 times G acting at an angle theta about the vertical. Acting at an angle theta about the vertical. Sorry. Acting at an angle theta about the vertical. And resolving the components of this weight, we have the horizontal component and vertical component. This component, it is M1 G cosine of theta, and this component down in the plane, it is M1 G then sine of angle theta. Also, we have the normal reaction, R. The normal reaction R. We have the normal reaction R. The normal reaction R1, call it R1. Likewise, for mass 2, its weight M2 times G, and the tension force T. Also, the component of this weight, which is M2 G cosine of theta, because the angle between the weight and the vertical, it is theta, the same as this angle. And the horizontal component, which is M2 G sine of theta, M2 G sine of theta, and the normal reaction R2. Now, because our motion is down with the plane. So we consider all forces acting in the direction of our motion. For instance, for mass 1, it is m1g sine of theta and tension T. And for mass 2, it is m2g sine of theta, tension 2. And the direction of our acceleration is down the plane. The direction of acceleration is down the plane. Sorry. So the free body diagram for mass 1, it is the force, there is tension force F, and the component of weight m1g sine of theta acting down with the plane, and its weight m1g, and the vertical component, which is m1g cos of theta, and the reaction R1. Likewise, for mass 2, it is tension force T, and its weight m2g, and its component m2g cos of theta, and m2g sine of theta, and the normal reaction R. Now, from Newton's second law of motion, for mass 1, the net force acting on mass 1 is given by mass 1 times acceleration. The net force acting on mass 1 is given by mass 1 times acceleration. Okay. But the force we consider here is the forces that acting down in the inclined plane. The force acting down in the inclined plane, which are m1g sine theta and tension force. And because our direction is down the plane, so m1g sine theta is the leading force. So this becomes m1g sine theta plus the negative of tension is given by m1 times acceleration A. This equation becomes m1g sine of theta, then minus t equals to m1 times A. Call this equation 1. Also for mass 2, the net force acting on mass 2 is equal to mass 2 times acceleration. The forces acting on the direction of the motion are tension T and m2g sine theta, which is tension plus m2g sine of theta equals to m2 times A. Now make it the subject. This implies that tension T equals to m2 times A, then minus m2g sine of theta. Substitute this equation into equation 1 to obtain m1g sine of theta minus tension, which is m2 times A minus m2g sine of theta, then equals to m1 times acceleration A. Rearranging the equation becomes m1g sine of theta minus m2a plus m2g sine of theta equals to m1 times A. Okay. Assemble the similar expressions, for instance, for acceleration A. This becomes m1g sine of theta, then plus m2 g sine of theta equals to m1 times a plus m2 times a, making a the subject, or commutating this equation becomes a in bracket m1 plus m2 equals to g sine of theta in bracket, then m1 plus m2. Now making a the subject of the formula, we get therefore a equals to g sine of theta, then m1 plus m2 out of m1 plus m2, but we cancel the total mass, for each. The expression becomes a equals to g sine theta. This is also known as the sliding acceleration. The sliding acceleration of the system.